All right, next up, magnetism. Magnetism has a couple of equations to try and balance. The main ones are going to be, we'll go ahead and get started with those, the Lorentz force. Now, technically, the Lorentz force has another term in there, but for the most part, all you really need are the ones that I'm showing here. I always mark it as F sub B. As I've mentioned in class, the standard for magnetic fields is B, a capital B. So anytime I'm dealing with magnetism of any kind, I pretty much always put B there. Now, you may also see, because a standard one is also to use a capital M for magnetism. Your mileage may vary. Knock yourself out. Again, you can remember it however you'd like, but B is how I do it. Okay? It also helps you keep track of that it's based on magnetic fields. This is a magnetic force, and magnetic fields are pretty much always a B. So, Lorentz force on a charged particle, because we have two different versions of this. QV B sine theta. Where this is our Lorentz force. Q is our charge. This is on a charged particle, so you have a proton flying through a magnetic field. So you'll have the charge of whatever your particle is, times its velocity, how fast it's going, times the strength of the magnetic field, times sine of the angle between them. Where in this case, the angle between them is going to be the angle between your velocity and your magnetic field. Okay? Now, you'll notice that I've also got this guy marked that he is a vector. That is where our right-hand rule comes in. Now remember, I also mentioned that this came from a cross product, something a little more than what we need to remember, but I'll bring it up here. QB cross B. The reason that that's useful is the rules that we had were we point our fingers of our right hand, not left, right hand, in the direction of our first vector. So whichever way our velocity is pointed, we point our fingers that way. Let's say it's to the right. Our magnetic field, let's say that it's pointed up. Nice uniform up field. I can't point my fingers, I try and curl them up towards it, but I can't, so I have to flip my hand. Now I can do that. Now I curl my fingers up, which way my thumb points, that is the direction of the force. If I had a charged particle, a positive charged particle I should say, moving to the right with a magnetic field up, it would feel a force out of the board. A negative just goes the exact opposite direction, so just keep track of that. Next one, the other form of this is going to be FB equals ILB sine theta. Where I, this is the force on a current carrying wire. Okay? I is the current going through the wire. L is the length of the wire that we are looking at. B is our magnetic field. And again, sine theta. So again, in this case, you will have I, point your fingers in the direction of the current, you'll curl them towards the magnetic field, and the resulting direction is the force on it. This is one of those points where, this is one of the solid reasons why we don't change out the current, even though we know it's a negative charge moving in a given direction, we just keep it here as defined as the positive charge, so that everything still works out swimmingly. Okay? So, again, you'll end up with the same force, it's just that was the convention, so they kind of stick with it. There are a couple of other things that actually show up that reinforce it as well. These are Lorentz forces. This is the force on a charged particle moving through a magnetic field. This is the force on a current-carrying wire in a magnetic field. All right, so the next one. Next thing that we need is the magnetic field created from a current-carrying wire. Moving charge creates a magnetic field. So our magnetic field that we create from a wire is equal to mu naught, which is the permeability of free space. Basically, it describes how easily a magnetic field can go through it. It's not quite that, but that's good enough for what we need. Times our current in the wire divided by 2 pi r. Now for APC, Be familiar with how to derive this. It's a very simple derivation using Ampere's law. Okay? So, this is one of the main ways that we can actually find the magnetic field created by a current carrying wire. We use the modified right-hand rule with that one. We point our thumb in the direction of the current, and we curl our fingers around, and that tells us which way the magnetic field goes. Remember, magnetic fields always come in closed loops. Always, always, always. According to our current understanding of physics, there is no such thing as a magnetic monopole, no matter what some researchers may have proven with a supercomputer and some weird simulations. Now, one of the things that I saw was, just because this is the only equation that we're solving for a magnetic field, where this is an equation for a magnetic field, that does not mean that anytime you're looking for a magnetic field, you must use this equation. Remember, your magnetic field shows up as variables in these two. It is entirely possible, if they ask you for the strength of the magnetic field, or if I ask you for the strength of the magnetic field, maybe you can get the force from somewhere else. No, you're supposed to stay there. Oh no! Okay. Right. Maybe you can get the force from somewhere else, and you'll know the charge and the velocity. Basically, you know everything else. You can solve for B, your magnetic field, using these. Just because this equation isn't set up where it's B equals some stuff, doesn't mean you can't solve for your magnetic field there. This is very useful, but it's not always the case. I saw some questions where it was actually a charged particle moving through a magnetic field. They asked you for the strength of the magnetic field, and I saw a number of people use this. This is only for a current carrying wire, not charged particles. Next equation. Greek letter, capital Phi. And again, I always use a sub B for magnetic. It turns out that flux is an idea that can be applied to actually quite a few different things. Although we really only deal with it specifically by name in magnetism, at least at this level, because there's an actual thing that we get from our flux. For APB, it's going to be our magnetic field times our area that magnetic field is applied on, times cosine of the angle between them. Now, the important thing on this, because we need vectors for angles between them, is the idea of an area vector. Okay? So, if I've got the area of this notebook, my area vector actually points off of it at a right angle to it. This is one of the more confusing things, because a lot of people will remember that this is a maximum when they're pointed like this, and they think that this becomes a sine. It actually comes from our dot product that simplifies down to a cosine, but it's this new idea of an area vector where we can perfectly describe the orientation of our surface in space by this one vector that points that way. It becomes difficult, so for instance, if I just had it pointing along one side, maybe pointed straight to the right, I could have this, I could have this, I could have anything in between. That vector is always pointed to the right. Same thing with up. I could rotate it all around this where I've got it all over the place and I can't fully define it. But if I've got an area vector, as we actually use them, where it's at a right angle, if I tilt this a little bit, that changes this vector. That's why we use those. Okay? Flux. Magnetic field strength, stop that, times our area, times cosine of the angle between them. Now usually what you're going to encounter is we're going to set it up where we have the maximum flux through there, although sometimes there could be a conceptual question where you have to figure that out. And so it coming in will be at a right angle to it. Oftentimes this guy's going to evaluate to 1. Not always. We talked about how real generators actually twist a loop of wire, usually, to induce a current, which is where we're going next. The broad equation is our EMF. It's written both of these ways. Equals, broadly it is negative delta phi, so our change in flux over change in time. That is the not quite complete because it needs to be an actual differential calculus-based one. But this is more in general. This tells us as we change our flux through time, we will actually develop what's called an EMF, an electromotive force. And I cannot stress this enough. Whenever you are dealing with an EMF, you can set it basically equal to a voltage for your circuit. That way you can find the current induced in the wire and so forth. Functionally, this guy operates exactly the same as a voltage. In fact, the units that you get out of this are in volts. Now, one of the main ones that we used in APB is actually having a loop of wire in a magnetic field, and it's moving out of that uniform magnetic field at a given velocity. That EMF looks like this. It is the magnetic field strength, so B, the intensity of our magnetic field, in Tesla, L, the perpendicular length of the wire, and V, our velocity. Double check the videos that I put up online. We did some pretty, not in-depth ones, but a pretty good explanation of this particular equation. That's the main one we're dealing with, though conceptually it's important to understand this. As we change our flux, our magnetic flux through an area, in time, we will actually create this voltage and be able to start moving charges around. All right. The key to this, a couple of conceptual notes. First off, right-hand rule. We've talked about it. Review it. Make certain you know how to use them and that you have enough practice with it that you are comfortable that you are not going to use your left hand. Do not lose points for a foolish reason. Right hand, always right hand. Okay? Next up. Moving charges create magnetic fields. And finally, a changing magnetic field will actually create an electric field. It's harder to see, but that's actually what this equation is saying. We treat it as a voltage because functionally it's a lot easier for us to work with that in a circuit. But in the end, as I said, this electromotive force describes pushing charges around, making them start to move. When you're talking about forces on charged particles, you end up talking about the fields, not the voltages. We talked about that before. Force is related to electric field. Again, this is one of those places where it shows back up, that conceptual understanding. And these two working together, a changing electric field, moving charges, creates a magnetic field. If you have those accelerating, then I'll have a changing magnetic field, which creates a changing electric field, which creates a changing magnetic field, which creates a changing electric field, and so forth and so on. We call that electromagnetic radiation, and that is light, among other things. So, that is a broad overview of magnetism. Key things are going to be right-hand rule, and being able to keep track of when it's a current-carrying wire or when it's a charged particle. One of the final things that I will say on this, actually a couple things now that I think about it that I didn't have jotted down. One, because of the nature of the cross product, the actual force that the magnetic field applies on a charged particle is always at a right angle to which way it's going. We talked about maybe the velocity is going off here to the right, our magnetic field is up, so we feel a force out of the board. As it starts coming out of the board, now my fingers are pointed this way, kind of out of the board some, and then curling up. Now it's at a right angle. Again, as you go through, it will always be at a right angle to the way it's moving. Double check your work equation, because what that means is, while it's constantly 90 degrees, no work can be done by a magnetic field and the force on a charged particle. In other words, it will move in a circle, but it will not speed up or slow down. One of the final things on this, so that's an important concept. Magnetic field cannot do work, and it's all related to that work equation and the angles involved. Now the final thing that I'll mention on that is, because it will make a charged particle move in a circle, anything moving in a circle has you're probably groaning, but when you stop groaning, you will say it has a centripetal force, which is equal to mv squared over r. Because the thing that is making that, the only force acting on it as it moves in the circle through the magnetic field is the Lorentz force. You'll find that your sum of forces is going to be equal to my Lorentz force, and therefore must be equal to my centripetal force, mv squared over r. I do that replacement. We're talking about a charged particle here, so qv b, assuming that the angles are at nice right angles, equals mv squared over r. This is one of those keys where, again, You can find the magnetic field based on a charge moving off in a circle, not by using the equation that I mentioned before where it has, hey, a magnetic field, because that's not a charged particle, but by relying on it showing up in your Lorentz force. You'll find that you can have a relationship. Once you've got this set up, which is literally identifying, hey, it's moving in a circle, and my Lorentz force is my only force, and therefore my centripetal force, you can plug in whatever you want and solve for whatever else you need. Okay? So, that's magnetism.